Hi everyone, welcome. Today we are going to discuss about electrochemistry. We are starting electrochemistry today. In this class we are going to discuss about what and why, what is electrochemistry, definition of electrochemistry, and why we need to study electrochemistry. This is the first target. Second target, conductance and types of conductance. Generally in conductance we will go through three steps. The first one, what is conductance, what is the type of conductance, right? Definition. Second, the formula of conductance. Third, units of conductance, right? Okay, so the first point is, what is electrochemistry? So the electrochemistry is nothing but the relation between electric current, electricity, and the chemical reaction is nothing but electrochemistry. The relation between electric current and chemical reaction. What it is? Simple. Generally in our daily life, so many things we see, like refrigerator, like water purifier. These are all things we generally see in our home. For suppose if you take water filter, right, we generally give electric current to that to work water filter properly. So it takes electric current first and it takes water from the water tank. What it is doing? It is doing some work. So chemical reaction is performing in the water filter, right? So it is taking electricity, and what happens? Dirt is removing from the water. Unwanted minerals removing from the water. So these are all things, these are all chemical reactions, chemical changes are occurring, and it is giving pure water to us. So these are all things are happening because of electrochemistry. So that's why we have to study electrochemistry. So the relation between the electric current and the chemical reaction is nothing but electrochemistry. So this is what is the definition of electrochemistry and why we have to study electrochemistry. Okay, now we are moving with conductance. So what is conductance? That's the point. What is conductance? That's the point. Simple. See here, I'm taking one cell, right? I'm taking one cell. In this, one electrolyte is there. Let us say NaCl electrolyte. This is NaCl electrolyte, right? This is NaCl electrolyte. Now what happens? Na plus and Cl minus ions are there. Now I'm taking two rods. They are nothing but electrodes. We say whenever we have the rods in this electrolyte solution, we have two rods like this, right? So these are nothing but electrodes. So one is, let us say, positive rod. This is the positive rod, this is the negative rod, right? So these are nothing but electrodes. So these electrodes are placed in electrolytic solution. Then what happens now? Here in electrolyte, Na plus ions are there and Cl minus ions are there. Na plus and Cl minus ions are there. Now positive ions, the positive charged species, are moving towards negative electrode. Why? Because of force of attraction. Negative ions are moving towards positive electrode because of force of attraction. So what happens? Ions are moving. Okay, so positive species are moving, charges are moving. So because of moving the charges, it is conducting electric current. Okay, so if the rate of flow of these charges, are high, conductance will high, because whenever rate increase, they will conduct more electric current. So conductance increase. So the conductance is nothing but, so what is the conductance? What is conductance? That's the point. So conductance is nothing but, so the definition of conductance. So the definition of conductance. rate of flow of charges, rate of flow of charges is nothing but conductance. Rate of flow of charges in electrolytic solution. In electrolytic solution. Electrolytic solution is nothing but conductance. Rate of flow of charges in electrolytic solution is nothing but conductance. This is the definition. So this conductance is represented with generally G or we can say C, but in most of the textbooks it is represented as G. Okay, so this is the definition. Then what is the formula? What is the formula of conductance? Simple. The formula of conductance is conductance equal to 1 by resistance, because resistance is nothing but, conductance is nothing but flow of current. Resistance opposite, so the current will not flow. So conductance is inversely proportional to the resistance always. Okay, so conductance G equal to 1 by R. So this is the formula of conductance. This is formula of conductance. Now resistance units. What are the units? Units 1 by R equal to 1 by ohm. 1 by ohm. So ohm equal to, I can write 1 by ohm equal to ohm inverse. So this ohm inverse also called as Siemens. Ohm inverse also called as Siemens. So this is important. So the unit of conductance is Siemens. The unit of conductance is Siemens or ohm inverse. These points are very, very important when you try to solve the questions on electrochemistry. In next classes we are going to do the questions, so pay attention here. Okay, so this is very important. Conductance equal to 1 by resistance, and the units of conductance is Siemens. Unit of conductance is Siemens, and this is the definition. Now what is specific conductance? What is specific conductance? What is specific conductance? Specific conductance is also called as conductivity. Specific conductance is also called as conductivity. Specific conductance. Specific conductance. Specific conductance or conductivity. Simple. Again the same definition, but the only thing changes the rate of flow of charges in electrolyte solution is conductance. There I didn't mention any specific amount, but here specific conductance or conductivity is represented with kappa. This is the one thing. Next one, what is the definition? If the rate of flow of charges in 1 centimeter cube area of the electrolyte solution. Electrolyte solution is same, but I'm taking specifically 1 centimeter cube area. If you take this cell again, I have two rods here. This is the electrolyte solution. Now, in 1 centimeter cube area of this electrolyte solution, how many charged species are running or flowing? So the flow of charges in 1 centimeter cube area of solution is nothing but your specific conductance or conductivity. Specific, nothing but 1 centimeter cube area. So in 1 centimeter cube area, okay, the rate, the speed of charges you have to measure. That is nothing but your specific conductance. Definition is okay. So the rate of flow of charges in 1 centimeter cube area of electrolytic solution is nothing but your specific conductance or conductivity. So this is the definition. Now what is the formula of this? Conductivity equal to 1 by resistivity. Conductivity equal to 1 by resistivity. If you can find out this resistivity, then you can get the answer, you can get the formula. Then we know conductance equal to 1 by resistance. Conductance equal to 1 by resistance. Okay, now you have to know here, you have to know one thing here. Resistance is directly proportional to the length and inversely proportional to the area. So combinedly I can write as R is proportional to L by A. So why? What is the reason? Why resistance is directly proportional to the length? What is the length? Length is nothing but the distance between the two electrodes. The distance between the two electrodes, this is nothing but your length. Okay, and this part is nothing but your area. Okay, this is nothing but your area. This is the distance between the two electrodes is nothing but length. Okay, so why resistance is directly proportional to the length? That is the question. Now, first suppose you take a long wire. Okay, now in this wire, a metal wire, positive ions and negative ions are moving in opposite direction, like this. Positive and negative ions are moving, right? Positive and negative ions are moving in opposite direction. Okay, so if the speed or rate of that ions increase, conductance increase. Now what happens whenever length increase, conductance, they will collide with each other. What happens whenever length increase? Collision between the species, charged species, increase. Okay, so whenever collision increase, speed will decrease. That means conductance will decrease, right? When conductance decrease, resistance increase. Okay, so when length increase, collision between the charged species increase, speed decrease. Whenever speed decrease, conductance decrease, because speed directly proportional to the conductance. So whenever conductance decrease, resistance increase. So resistance is directly proportional to the length, area. How can you explain this? First, suppose 10 members are there in one room. 10 members are there in one room. It is a small room. If area of room increase, then they can move very freely. Initially, very small room, they cannot move that much. But whenever you have a large room, then those 10 members can move very freely. So speed of those persons will increase. In the same way, whenever area increase, speed of ions increase. When speed increase, conductance increase, resistance decrease. So resistance is inversely proportional to the area. So R is proportional to L by A. We can write. So R is proportional to L by A. R is proportional to L by A. Okay. Now, if I remove proportionality constant, R equal to rho into L by A. Why? Rho is the proportionality constant, right? So now rho equal to, I can write RA by L. So this is R rho. Clear? Now we have this formula. Put this rho here. Rho equal to RA by L. Rho equal to RA by L, right? RA by L. I can write L by A into 1 by R, L by RA, L by A into 1 by R. Now this L by A, length by area, is nothing but your cell constant. Okay, L by A is nothing but your cell constant. Cell constant into 1 by R, conductance equal to 1 by resistance. I already said this. So I can write conductance. So finally I can write conductivity equal to cell constant. Conductivity equal to conductance into cell constant. So this is one formula. So one formula is this. Conductivity equal to LR by A, and conductivity equal to conductance into cell constant. So this is one formula. Conductivity equal to this into this, and conductivity equal to conductance into cell constant. Okay, now what are the units? Of this? We know conductivity equal to conductance into cell constant, L by A. Cell constant is nothing but L by A. Okay. Now, conductance, we know Siemens. Conductance, units of conductance is Siemens. Length is nothing but centimeters, area centimeter square, right? Okay. Now Siemens centimeter inverse, or if you take meters here, then you have to take meter square, or Siemens meter inverse. So conductance unit Siemens, specific conductance or conductivity units Siemens centimeter inverse or Siemens meter inverse. So the units of this Siemens centimeter inverse or Siemens meter inverse. Next, molar conductance. So what is molar conductance? What is the definition of molar conductance? Molar conductance. So what is the definition of molar conductance? Again simple. The rate of flow of charge. Again, the rate of flow of charge of 1 molar electrolyte solution. If the concentration of electrolyte is 1 molar, then the rate of flow of charge. Again, the rate of flow of charge in 1 molar concentration of electrolytic solution is called molar conductance. So this is represented with lambda m. So lambda m equal to kappa conductivity by concentration, which is in molarity. Okay, so lambda m equal to kappa by concentration. So this is conductivity units Siemens centimeter inverse by molarity. So molarity is nothing but, if you know the definition of molarity equal to number of moles of solute over volume of the solution in liters. Here it is centimeter, so you have to convert liter into centimeter. We know 1 liter equal to 10 power minus 3 meter cube, 10 cube centimeter cube, right? So 1 liter equal to 10 cube centimeter cube. So I can write this. So centimeter cube, you have to take in centimeters. So molarity equal to number of moles by number of moles of solute by volume of the solution. It is centimeter cube. Okay, so what happens? Siemens centimeter inverse centimeter cube. So I can write centimeter cube by mole, right? So Siemens centimeter square per mole. Right? So this is the unit of molar conductance. Now equivalent conductance. What is equivalent conductance? Only thing change, instead of 1 molar concentration, we take 1 normal concentration. So the rate of flow of charge in 1 normal concentration of electrolytic solution is called equivalent conductance. So now equivalent conductance lambda eq equal to kappa again by concentration now in normality. So normal. Okay, in normality. Now normality equal to number of moles of solute. Instead of number of moles of solute, we take number of gram equivalent of solute. So number of gram equivalent of solute over volume of the solution. So volume of the solution is same. In place of mole, you have to take gram equivalent. So gram equivalent, number of gram equivalent of solute by volume of the solution in centimeters, right? So now I can write this as Siemens centimeter square gram equivalent inverse, in place of mole inverse, gram equivalent inverse. So this is the unit of equivalent conductance. This is the equivalent of the unit of equivalent conductance. Okay, now the relation between the relation between molar conductance and equivalent conductance. Relation between molar conductance and equivalent conductance. So what is the relation? We know lambda m equal to kappa by molarity, lambda eq equal to kappa by normality. So lambda m by lambda n you have to do, right? So lambda m equal to kappa by m by kappa by n, that is n by kappa, get cancelled. So normality by molarity, normality by molarity. So lambda m by lambda eq, lambda m by lambda eq, molar conductance over equivalent conductance. So molar conductance over equivalent conductance is n by m, right? Molar conductance over equivalent conductance equal to normality by molarity. If you have a little bit idea on mole concept, normality equal to, I can write n factor into molarity. What is n factor? M factor into molarity, right? By molarity. So molarity get cancelled. So lambda m by lambda eq equal to n factor. So I can write lambda m by lambda eq equal to n factor. Lambda m equal to n factor into lambda eq, equivalent conductance. So this is the relation. So molar conductance equal to n factor into equivalent conductance. Then what is n factor? Simple. N factor is nothing but, if you have the positive ion, for suppose Zn plus 2, right, the charge is nothing but your n factor. Here n factor is 2. If you have Al plus 3, then your n factor is 3. If you have Mg plus 2, your n factor is 2. If you have Cl minus, your n factor is 1. Your n factor is 1. And always n factor you have to take mod. Even it is minus 1, you have to take minus 1 in mod. So you have to write plus 1. Okay. So this is about your n factor. For suppose you have salt. Na2CO3. Na2CO3. So I can write 2 Na plus 2 Na plus CO3 2 minus, CO3 2 minus, right? So n equal to 2, right? N equal to 2. So the charge is 2 here, right? NaCl, Na plus Cl minus. That means if you have the salt, you have to take total positive charge or total negative charge. Total positive charge here 1, so n equal to 1. Or consider total negative charge Cl, so n equal to 1, right? So this is how you can calculate n factor. You can find n factor. So this is about the today's class. Okay, I hope you enjoyed the class. So that's all. Thank you so much for watching. Bye bye.